How's everyone going? Professor Bryant with another installment of mini lectures. This one specifically about showing you the expanded Lewis structure for multi-central atom molecules and showing you what the condensed format looks like. This is really helpful for those of you all who are going to be moving into organic chemistry and to give you kind of some practice on how those molecules are drawn in that course, which is starkly different from how we are drawing molecules in this course. So if you take a look here at the expanded versus the condensed form of different molecules, what I have shown you are pretty straightforward carbon molecules, and then in one case we have carbon, hydrogen, and oxygen. But what we have is hydrocarbons, and then in some cases carbohydrates. And I have shown you the expanded version right here. We see the expanded version, which has 1 and 2 carbons singly bonded to one another with 3 hydrogens bonded on each of those carbons, right? Specifically speaking, this would be C2H6, right? We would label it the molecular formula, right? We should be familiar with how to do that. Now, if I was to show you this expanded version on, let's say, an upcoming assessment, I would expect you to be able to tell me a couple different things about its molecular geometry at the carbon. I would expect you to be able to tell me the bond angles between each of the atoms. I would expect you to be able to tell me, or the bond angles between each of the bonds on any of the carbon atoms. And I would expect you to tell me a little bit about the hybridization, the type of bonding that's occurring, and all of these things you should be able to do after watching my video on bonding and hybridization and after we touch on those topics in class. But this video is more to show you how organic chemists, instead of writing out all of these letters, writing out hydrogen 6 times, writing out carbon 2 times, organic chemists use the condensed format, which you'll see on this side, as their way of bypassing a lot of writing. This is simplifying the process of drawing molecules. Notice what I have written for you here is a straight line. That straight line is the condensed format for the hydrocarbon I have drawn on the left in the expanded. Okay, so if we wanted to call this example A, example B, and example C, this is example A in condensed format. This is actually what we call ethane, okay, ethane. And we're not so concerned with the nomenclature part of this. You'll get into that more so in organic chemistry. But ethane is represented as a straight line. A couple rules to this, major rules here. One of them is that hydrogens are never shown. We assume that they are there if carbons are there and no other atom is attached to it. So we don't see any nitrogen, we don't see any oxygen, we don't see any sulfur, we don't see any fluorine, chlorine, bromine. Therefore, hydrogen is assumed to be there. And we always assume that carbon has its full octet fulfilled whenever we draw it on our paper. So in organic chemistry, and specifically in a lot of general chemistry, carbon is going to be seen most of the time as a fully fulfilled octet. It's going to have either 4 single bonds, 2 double bonds, 1 triple bond, and 1 single bond, etc. Okay, 1 double bond and 2 single bonds. There are multiple ways to fulfill carbon's octet. In this case, what this condensed form of one line is actually representing 6 hydrogens, where 3 are bonded to carbon 1 and 3 are bonded to carbon 2. Notice I have labeled each end of this straight line with the values 1 and 2 to represent where those carbons are. Okay, let's take a look at example B then. If we add 1 more carbon, from a structural standpoint, we are now dealing with propane, which we are familiar with as a gas that's utilized for cooking and heating. Propane now is C3H8. But notice in our condensed formula, we are only showing two straight lines. Notice that these two straight lines are bent or not bent. They have a angle associated with those two straight lines at the meeting point, which is carbon 2. And the reason for that is because each of these carbons has a tetrahedral geometry around it. So the bond angle of our condensed formula should be exactly the bond angle that we expect from a tetrahedral molecule, which is in fact 109.5. And that's not the purpose of this video, but it's great to see that that overlaps and that concept overlaps to help students understand why we do not just draw this as a extended straight line. We should not do that because that gives us some insight into there being three carbons, right? This is incorrect because this is still only showing us two carbons. So we do not want that. So notice here, we are not again showing carbons. We are also not showing hydrogens. We have really just condensed example B on the left to two straight lines connected. Okay, this is extremely, I know this seems maybe, simple, but this is extremely important for those of you all that are going to move on to organic chemistry. This will give you a heads up or head start, if you will. So now let's look what happens when we start to add in atoms that are not carbon or hydrogen. In the case of atoms that are not carbon and hydrogen, we need to use the chemical symbols. And those chemical symbols are directly from the periodic table. So for oxygen, O, for nitrogen, N, for chlorine, Cl, fluorine, F, so on and so forth. Notice now I am showing the expanded version with carbon having a double bond to the oxygen. I'm showing the lone pairs on the oxygens, and I'm showing octet fulfilled on all carbons, and I'm essentially showing a dimethylformaldehyde is what this molecule is, if I'm not mistaken. But the condensed formula, which alleviates us from having to draw a C or H, is shown here. Notice I've labeled the carbons once again. I have not labeled the oxygen because the oxygen we know is on carbon 2 based on the expanded formula. And this drawing here is now the correct structure. Notice that carbon in the second position only has 3 electron domains around it, 3 bonding domains. So we now expect this bond angle to be different from the bond angle in example B, particularly because it now has a molecular geometry around carbon 2 of trigonal planar, right? So see how the concepts that we learned in VSEPR, or valence shell electron pair repulsion theory, can carry on into bigger molecules, because as you get into organic chemistry, all of the molecules are going to have multiple central atoms, if you will. Okay, so this is a great example of that. Now these can get more complex, and we'll move to some higher complexity. What happens when we put in a nitrogen? Well, nitrogen, to have its and let's also speak on this really quickly before we move on. You do not show the lone pairs on the condensed formula. However, you can. It's not incorrect if you do, but generally speaking, you don't necessarily have to. They are assumed to be there. Again, even oxygen, we assume octet is fulfilled. Unless we are showing a formal charge, we assume octet is fulfilled. And even then, formal charge, we can have octet fulfilled and formal charge can be there. So what happens with nitrogen? Well, generally speaking, nitrogen can contain 3 bonds with a lone pair to have octet fulfilled. So what we have here is 3 carbons in the expanded with a nitrogen attached to the one of the end carbons, and we will label from that end, and you'll get into that further when you talk organic chemistry nomenclature. but that would be the first carbon, second carbon, and third carbon labeled as you see here. In the condensed version, and notice we are showing the nitrogen and we are showing the hydrogens attached to the nitrogen, okay? So whenever the atom is a non-carbon, we do show hydrogens attached to the non-carbon atom, as you see in this case. And this is 1-amino propane, okay? 1-amino propane. So NH2 is an amine group, so we call it amino. In the case of a double bond, notice that we're showing in this next example, and this will be example D and E. We show a double bond. Now, the molecular geometry around these central atoms changes when a double bond is involved, and so does the bond angles, right? Again, whenever it's tetrahedral, as we see in example D, everything has tetrahedral electronic geometry for bonding domains around it. But in the case of these carbons that are doubly bonded, that is not the case. And notice what we see over here. We see a double bond, and then we see straight lines representing the rest of the carbons. But here we have an oxygen, or what we call an alcohol group. And that alcohol group specifically gives us an oxygen that we have already seen oxygen, but it gives us an oxygen specifically at the end of this molecule, and it is not doubly bonded, so there is a H attached, and notice that we show the H there as well. We do not assume H's on atoms that are not carbon. So in this case, this is an alcohol group, okay, and we would call this I think it's called propenol, or 2-propenol, 2-propenol. There's a couple different ways to name these, and you'll get into that when you get into organic nomenclature. But condensing these formulas can be fun, it can be interesting, and it also is going to benefit those of y'all, especially those of y'all who are trying to do pre-med organic chemistry. That tends to be a place where a lot of people find them still struggling. Now, let's talk about molecules that are not chain molecules, but potentially what we call cyclic or cyclic, meaning that they are connected to one another. In this case, notice we have 5 carbons all singly bonded to 2 carbons, while singly bonded also to 2 hydrogens, fulfilling their octet. And now we have a pentagonal shape, right? And this pentagonal shape via Lewis structure is shown here in this condensed formula. Notice the hydrogens are not there. And notice that the bond angles here will be a little bit different. And you'll get into the cyclopentane, which is what this molecule is called. You'll get into the 3-dimensional structure of cyclopentane furthermore when you get into organic chemistry, but recognize that these are still effectively tetrahedrally shaped, tetrahedral molecular geometry around carbon, because once again, 4 bonding domains. The next molecule here is benzene, what we call benzene, which is 6 carbon atoms in a cyclic structure. However, there are double bonds at 3 positions, okay? And these positions can be labeled, if we needed to label them, as 1, 2, 3, 4, 5, 6. So there are double bonds at position 1, which what we would say at 3 and at 5. However, this molecule is equivalent even if those positions were changed and moved to double bonds at position 2, 4, and 6. Hopefully we can see that. These are still the same molecule. Even if we did not rotate the hexagon, if you will, if we rotated the bond position. And this is similar concept to what we talked about in resonance, right? And this would be a good time to talk about resonance as we remember resonance, right? Let's use an example of a Lewis structure that we're familiar with. So let's take a look at carbonate, right? CO3 2 minus. If we go by our methodology of valence electrons, 4 plus 6 plus 6 plus 6 plus 2 equals 10, 18, 24 valence electrons. We put carbon in the center. We create 3 single bonds to oxygen. We use 6 electrons. We left with 18. We use lone pairs on the most electronegative, 6, 12, 18. With our lone pairs, that leaves us with no electrons left. We must create a double bond because our current formal charges exist as 3 negatives and 1 positive, giving us the same formal charges of our original molecule. We can then create a double bond. Let's say we create one here. That gives us formal charge now on the most electronegative atom, which is the 2 oxygens that are singly bonded. And now we have the final Lewis structure, right? We have the correct Lewis structure. If we want it to be thorough, right, we have 3 electron domains, 3 bonding domains. We have trigonal planar molecular geometry and trigonal planar electron geometry. So molecular geometry is trigonal planar. Okay. If we want to take it a step further, we have sp2 hybridization on the carbon. Okay. Why? Because there's 3 domains. We should also expect what bond angle? 120 degrees. Because of 3 domains, right? All of this you should be able to do. And now let's talk about resonance, okay? If we labeled each of these oxygens as 1, 2, and 3, there are technically 3 different Lewis structures that could be drawn where the double bond exists on 3 different oxygens at any given time, which would leave us with 3 different Lewis structures, okay? All still sp hybridized, all still with the same bond angles, but in different positions, right? In different positions. Double bond in position 1, double bond in position 2, double bond in position 3. Okay, so these are 3 resonance forms. In the case of our benzene molecule, there's 2 resonance forms, right? These 3 resonance forms effectively all exist at some percent, 33.3% at any given moment, which means that the second bond, or that extra pair of electrons that are involved in bonding, is actually what we call delocalized. And that delocalization is what causes this molecule to actually look a little bit more like this. And to give you some insight, if we drew this as a condensed structure, what would it look like? It would look like this. Okay, that would be carbonate as a condensed structure, but the resonance form of carbonate could also be drawn like this, right? Because that delocalization of that electron exists at all points, okay? However, generally speaking, you'll see this and you'll see the question ask you to draw this. Essentially, draw all of these just as we did before with the double bond in the 3 different locations, okay? So here we have the 3 resonance forms of carbonate in the condensed structure, all right? And that's kind of the premise of where we need to be able to get to, okay? From the Lewis structure, formal charge, fulfillment of octet, determination of hybridization, knowing the electron domains, bonding domains, knowing the molecular geometry, knowing how many resonance forms and if they exist, and being able to draw them in also the condensed format, right? Recognizing that this carbon itself is in the center, even though we have not written the elemental symbol there. Notice I'm also not showing the electron pairs, but recognizing that the formal charge there tells us something about how many lone pairs exist on each of these, right? These are the resonance forms, and it means that those electrons are delocalized, okay? All right, this has been another quick mini lecture on drawing molecular structures in the condensed format and a little bit on resonance. Any further questions, you know where you can find me. Feel free to email me.